Welcome back to Probability and Statistics. We are in Chapter 11 in this lesson from Elementary Statistics, 4th edition by William Navidi. In the last lesson, we looked at one sample hypothesis testing. So I've simply taken a sample, maybe weights of something, heights of something, whatever it may be, and we're simply testing whether or not the mean or proportion of that sample is greater than, less than, or simply not equal to some determined value. In this lesson now, we look at two-sample hypothesis testing, and it's exactly that. We're going to take typically two different samples and simply compare those two samples against each other to determine whether one sample is larger than, less than, or simply not equal to the other. As we look at the lesson outline, though, notice that there's two tests for means here, and those tests are just slightly different. One says it's a test for the difference of means, and the other says it's a test for the mean of the differences. So let me just quickly illustrate what that looks like before we get into the procedures and examples in this lesson. So in the first case, if I want to find the difference of means, what I'm doing is I've got two different samples. I've got sample A and I've got sample B. And I'm looking at the first sample A, and I'm finding the mean of that sample. Okay, we'll just call this mean of A. And then I have another sample, and I'm looking at its mean. We'll just call this mean of B. We'll call this sample B. And what I'm doing is I'm, again, comparing those two samples to each other. I'm wondering, is A bigger than B? Is the mean of A smaller than B? Things like that. So I might be asking, a question like that. Is the mean of A less than the mean of B? Maybe they're test scores, and I'm wondering if one section of students did statistically significantly better than the other section of students. So that would be an example of the difference of the means. I'm finding the two means, and I'm finding the difference of those two means. In the other case, where it's the mean of the differences, what I have here is typically a comparison of maybe like pre and post data. So if I continue with this idea of test scores, I might have student A who takes a pretest. Maybe it's a reading test, and I want to test the efficacy of a reading program. So they take a pretest, they get a 57, they go through this reading program, they take another test, and they get a 74. And then I've got student B who scores a 48 and then comes back and scores a 51. And I've got student C who scores a 62, comes back and scores a 77, and so on and so forth. Okay. In the second case, where we're finding the mean of the differences, what I would do is I would find the difference of each of those student scores. So student A, for example, would have a difference of 17, B would have a difference of 3, and C would have a difference, we'll just make that a 2, it looks like a 2, has a difference of 10. And then what I'm doing is I'm finding the mean of those differences. Okay, so those are the two kinds of approaches that we would take or could take when we're dealing with two different samples, or in the I guess two different samples, and wanting to talk about the difference between those samples, whether we're looking at the difference of the means or the means of the differences. All right, so with that, let's go ahead and get going here. So again, we're going to start with the hypothesis test for the difference between two means. So again, this is where we have the two different populations, and we are finding the difference of those means. Okay, so we're taking the mean of one population, or sample, I should say, the mean of another sample, and we're looking at those differences. As with the hypothesis testing previously looked at, we do have assumptions here. Again, we've got the random sample, we've got the central limit theorem. We want to make sure that our sample size is greater than or equal to 30, and that's for each sample that we'd have to look at that. Or again, ultimately, we just want to know that it's normal. So if the population is normal, we can assume that our samples would also be normal. And then the third one, which again, we don't typically state, but the samples do need to be independent of each other. So when we took the one sample, that can't affect the sampling for the other. All right, so as far as the hypotheses go, then again, we're going to use the H0 and the H1. H0 being our null hypothesis. And here now, because we have two different samples, we're going to call them mu1 and mu2 for their means. The null would be that there is no difference between those samples, that the mean of one sample is equal to the mean of the other sample. You might also sometimes see it written like this, where it's the difference of the two samples is 0. Obviously, either one works, they're both equivalent. And then for our alternative, again, as we saw previously, I might be asking, is the first mean less than the second mean? Is the first mean greater than the second mean? Or are the means just simply not the same? Oops, that should be a 1 here. So those are the three different alternatives that we could have. And if you think about kind of what's happening here then, if mu1 is smaller than mu2, what I really have is a left-tailed situation, because mu1 minus mu2 would be less than 0, would be negative. If I'm looking at greater than, I'd have a right-tailed situation. And if we're looking at just simply not equal to, we would have a two-tailed, where I'd be looking at both ends symmetrically. And so that would be a two-tailed situation. Just in terms of thinking about our picture and what area we're actually trying to find as we do these. Now, oftentimes this doesn't really matter when we think about this, the area, for example, and which side we're on. If I'm using a table, again, oftentimes a table will look to one side or the other. And so you have to be conscious of that, because sometimes you have to do 1 minus the value in the table. In most of the problems we do here, with mean in particular, we're going to be using a t-table, not a z-table. And t-table only has positive values. So it really doesn't matter which side we're on. We're really just looking at the almost kind of like an absolute idea, absolute value idea, where we're just going to look at the area regardless of which side it happens to be on. And we're just looking at the positive of that. We're looking at a positive value. All right, so we've determined our hypotheses. We again choose our significance level. We'll use the typical 0.05, 5%, unless a problem would say otherwise. And then we have to find P to determine whether or not to reject the null hypothesis. So here, again, as I mentioned, we're typically going to be using T, not Z, at least for the means. And so, again, because we have two samples and we're looking at the difference of the samples, when I find some of these values, a lot of these are going to be differences of the values. So I'm going to take the sample mean for the first sample minus the sample mean for the second sample, and then minus mu1 minus mu2. So statistic minus population, but here we're looking at differences, not just simply values. That second part, though, the mu1 minus mu2, because of our null hypothesis, we're assuming that that difference is 0. So in this formula, we are going to assume that mu1 minus mu2 is 0. And that will almost always be the case. There could be a situation, I suppose, where we assume that something other than difference being 0, but typically we assume a difference of 0. Whatever that assumption is, that's the value that we use there for mu1 minus mu2. And then we're going to take the difference of those differences and divide it by the square root of the standard deviation of the first sample squared divided by n1 plus the standard deviation of the second sample squared divided by n2. All right, so that formula gives us T, and then of course we can go to the table and we can find P from that table and then test whether or not we want to or have evidence to reject or not to reject the null hypothesis. One thing to note is when we go to the table, we've talked about the degrees of freedom in the past. Degrees of freedom, again, is the sample size minus 1. And so here also we need the degrees of freedom, the df equals n minus 1. But because we have two different samples, and those sample sizes often wouldn't be the same size, the question then is, well, what sample do we use? What sample size do we use? And in this case, we're going to use the smaller sample size. So of the smaller sample. So if I have two samples and one is of size 30 and the other is of size 20, we're going to use 20 minus 1 for our DF. Again, reason for that is we want the most conservative estimate possible, and the smaller our DF, the larger our T value, and the less likely it is that we are going to reject the null. The harder it would be to reject the null. All right. And then, of course, we make our interpretation and state our conclusion. So very, very similar process to what we saw in the previous lesson for the one sample. Again, some of the computations are different because we've got the two samples instead of the one. All right, well, let's take a look at an example then. And there's a lot here because, again, we're having to now deal with two different samples, so we have to clearly define both of them. But it says, according to a Stanford Business article, Americans may eat fewer calories at restaurants if the calories of the food items are labeled on the menu. All right, so it says, suppose researchers compared Starbucks receipts from locations where the menus were labeled to receipts from stores where the menus were not labeled. A random sample of 30 receipts from stores with menus labeled had an average number of calories of 225 with a standard deviation of 100. A random sample of 40 receipts from stores without menus labeled showed an average of 265 calories and a standard deviation of 75. Does this provide convincing evidence that the average calories per receipt at Starbucks with a labeled menu is less than at a Starbucks without labeled menus? Here we're going to use the 10% significance level. Okay, so we're curious to know, does labeling menus with calories actually change people's behaviors? Do they order food that has fewer calories or maybe less food to reduce the total number of calories that they are eating? So again, as we start this, we want to do our checks. And we want to make sure that we've got random samples, which they tell us they are. And we need to make sure that both samples are greater than or equal to 30. In this case, they are. We have a sample size of 30, a sample size of 40. And so again, that satisfies CLT, telling us that our two samples are both approximately normal, or that we can make that assumption. All right. And then we've got our hypotheses. So again, we always assume here that the two means are the same, that there is no difference. Whether or not we label menus with calories or not, that's not going to change people's behavior. They're going to order what they're going to order, and therefore we would not see a significant difference in calories per receipt. So that's our null. Our alternative is that there is a difference, and specifically here, if I define mu1 to be that the calories are labeled on the menu, so the calories are on the menu, and mu2 to be that the calories are not on the menu, so calories not on menu, then in this case, very specifically, we have this belief or this assumption that mu1 would be less than mu2. That's what we're really testing for. Will we find fewer calories per receipt for restaurants that label their menus versus those that don't? Okay, so now we are going to find T. And again, T is taking the difference of the means of the two samples. So if we look up at our information here, the average for mu1 was 225. That was with labels. And for mu2 without labels is 265. So we're going to take 225 minus 265. And not that we really need the parentheses, but it just kind of helps to see, okay, that's the sample part. And then we subtract mu1 minus mu2, which again, we are just assuming is 0. That's the population part. And now we divide by the standard deviation of the first sample divided by its sample size plus the standard deviation of the second sample squared divided by its sample size. So the first one had a standard deviation of 100, and that was the one that had a sample size of 30. So we're going to take 100 squared divided by 30, and then plus The second one had a standard deviation of 75, and its sample size was 40. So 75 squared divided by 40. All right. So I encourage you to actually calculate this. Make sure that you can get this all correct on your calculator or technology, whatever you happen to be using. But we should get negative 1.837 for our t-value. And a DF here, again, we always want to go to the smaller sample. So our DF is the smaller sample of 30 minus 1, which is, 29. Okay. Now, in the previous video, I did look at how to use the t-table, so I'm going to skip that here. But if we go to the t-table, remember that we're not going to find an exact value. So just real quickly here, if I go down to find a DF of 29, I'm going across that table to find positive 1.837. And if we look in the table and find that 1.837, we will see that the p-value is between 0.025 and 0.05. So between 2.5% and 5%. Now remember, we are testing not against the 5% level, but in this case against the 10% level. So clearly we're less than that. Our p-value is less than the 10%. And so therefore we reject the null. All right. There is convincing evidence. There is convincing evidence that labeling menus with calories reduces caloric intake per receipt, or calories ordered per receipt, or however you'd like to say that. But there is a difference, right? So if I label my menu with the calories, the evidence, at least as far as these samples go, would show that it does, right? There's a correlation of reduced calories ordered. All right, let's do one more just to make sure we've got this. And again, I would encourage you to pause the video and try this one on your own, see if you can get this, and then start it up and I'll go through the solution. But it says, does music help our ability to remember? To test this, 84 people were randomly assigned to two groups of 42 people each. Group A listened to music while attempting to memorize a list of words. Group B attempted to memorize the same list of words in silence. After 3 minutes of studying, people were given 1 minute to write down as many words as they could remember. Here are the summary results. All right, so again, Group A is the group that listened to music while they studied to see if that helped them remember, and Group B had no music. So just to kind of keep these straight. All right, do the data provide convincing evidence that memory improved while listening to music at the 5% significance level? Okay, so same process we went through before. Let's start with our checks. We want to make sure again that that our samples are random, and I'm pretty sure it just tells us right in there that they are random. Randomly assigned. So let me just make a quick comment here. Recall that when we do experiments, you can't force somebody to be part of an experiment. So you're not going to have a random sample because they have to volunteer. But in this case, what we have is random assignment, which is equally important. And so in this case, that's kind of our random sampling, if you will. And we just want to make sure that the treatments that are applied here, the music and no music, are two groups that are heterogeneous and not, somehow all related by some characteristic. And so the random assignment would do that for us. So we have random assignment, which is kind of the random samples that we typically look for. And in this case, we have two groups of 42, which is clearly greater than or equal to 30, and so CLT is satisfied as well. We can assume that our samples are approximately normal. All right, our null, again, is to assume that there is no difference, that whether or not people listen to music, that they are going to remember the same number of words. So here we will define mu1 as those who listened to music. So words recalled with music. And mu2 is going to be words recalled without music. It's very important that you define mu1 and mu2 because I could define this the other way. I could say that mu1 is without music and mu2 is with music. I would come up with the same results in the end, okay? But the order in which I subtract things is going to be different, and therefore, the process looks different, but ultimately I would come to the same conclusion regardless. But it's important that you define what mu1 and mu2 are, because now when we get to the alternative, again, in this case, it says, does the data provide convincing evidence that memory improved while listening to music? Again, I'm assuming that, or looking for evidence that mu1 is greater than mu2, that those who listened to music recalled more words than those who didn't. Again, if I flipped my definition for mu1 and mu2, I would have mu1 is less than mu2. Okay, so just be clear on that. All right, let's find t and then ultimately p. So here we've got the data is just kind of nicely laid out for us. So our difference in means, we want to take x1 minus x2, so 15.333 minus 13.714, and then minus 0, assuming the difference is 0, divided by the square root of 3.944 squared, divided by the sample size of 42, and then plus 3.550 squared, divided by its sample size also of 42. So that will give us a t-value of 1.977. Our DF here is obviously 41. Sample sizes are the same. Now, again, if we look in the table, there is no 41. So in the table, we'd be looking up a DF of 40 because that would be the next lowest number in the table. All right. And so from the table, and of course, you can use technology to do this, Excel, Google Sheets, graphing calculator. There's a lot of different technologies and actual statistical software programs. So, but if you're to use a table, find a t-table, you would find that p is, again, like our last example, between 2.5% and 5%. So p is less than 5%, our significance level. And so again, we reject the null. We have convincing evidence. We have convincing evidence that listening to music increases memory. Now, I should make a caveat here. A lot of the examples that I do in these videos are data that are taken from real life situations. Sometimes the numbers might be adjusted a little bit to make the problem work a little bit better. But this one is I will say completely made up. I just made this one up with just fake numbers and everything. So while sometimes some of these problems are actually legitimate in their findings, this one I couldn't tell you if listening to music actually increases memory, because, like I said, it is just completely a made up example. All right, so that's how we do a difference of means. We find the means of the two samples, and we're asking, is there a difference between those two means? So let's now look at the other situation for means, and that is the mean of the differences or matched pairs. So again, this is where I might have, where I'm often looking at an individual and I'm comparing data for that individual. So I'm looking at a difference between each individual's data points and then finding the mean of those differences. All right. So we've got the same assumptions as always. And again, for our hypotheses, everything is the same here as far as the work or pretty similar to it. So this is really more just to see and understand the notation. So here, when we talk about the mean of the differences, a lot of times you'll see mu sub d, or you might even see it written um, mu sub diff for difference. Okay, but it's the mean of the differences. All right. And in this case, we are assuming that that is equal to some initial value. And then the alternative is, again, just the fact that that mean of the difference is either less than, greater than, or not equal to whatever that initial value is. T here is now we're not actually taking the difference of two samples, so we're back to a simpler variation of the formula. We are going to take the mean of the differences for the sampled minus the initial value given, divided by the standard deviation of those differences, divided by the square root of the sample size. So that is our formula for finding t. Okay. All right. So let's go ahead and take a look at an example of this. Example says a sample of 5 third graders took a reading test. They then participated in a reading improvement program and took the test again to determine if their reading ability had improved. The table shows test scores for each student both before and after the program. Do the data provide convincing evidence that reading scores increased after the program? So the actual example I referenced earlier at the beginning of the lesson. All right, so we have 5 different students. We have their scores before they did the program. We have the scores after they took the program. So what we do in this case is, again, we're going to not find the mean of the before and after. We're going to find the difference for each student and then take the mean of those differences, the average of those differences. So if we just subtract these, student 1 improved by 8 points, student 2 by 5, student 3 actually went down 3 points, up by 1, up by 6. At this point, I would encourage just using some kind of technology, again, Excel, Google Sheets, graphing calculator, a statistical program, whatever that technology is, because we need to know not just the average, which would be easy enough to find, just add those together, divide by 5, but we also need to know the standard deviation of the sample. And again, you could find the standard deviation by hand, but that would be a bit of work. And so I would use some statistical software here. The mean of the sample or those differences is 3.4, and the standard deviation of those samples is 4.393. Now, just real quickly here, for those that maybe are just thinking, well, I don't know how to use any technology to find this. Excel, Google Sheets is usually what I kind of default to if I'm just doing quick statistical work like this. So in Excel, and I believe also Google Sheets, if you want to find the average, you're going to type this in right into your just 5 different cells in a row, in a column. It doesn't matter. Let's say I do A 1, 2, 3, 4, 5, and I've got it like that. Right, I've got my data in my Excel sheets or Google Sheets. I'm going to just type equals average. They don't use the word mean in these programs. They use the word average. And then in parentheses, A1 colon A5, because those are the cells I want to take the average of, assuming I put it in a column. And then for standard deviation, very similarly, it's equals, I believe it's std.dev for standard deviation. If you just start typing in std for standard, you will see something pop up. Actually, as I'm saying that, I recall now, I think it's std dev, because then there's a .s and there's a .p. And you want to make sure that you use the .s for sample, not the .p for population. So that's actually what the notation is. It's ST. I think there's one D for deviation. I don't think there's a second D there. And then again, same thing, A1 to A5, because we want to find the standard deviation of the values in those cells. Okay, so that would be how you'd use Excel or Google Sheets. Again, I believe this is the correct notation, as if I recall correctly. But if you start typing in STD, you will see it. Again, just make sure that you choose the .s and not the .p. All right, and you should get those numbers then that I have written down here on the screen. Okay, so our checks. We want to make sure that we've got random samples. Now, in this case, again, this is more of an experiment, and really just kind of a situation where we're just testing children against their own scores. So we're going to assume, in this case, because we really don't have enough information, we are going to assume that it's both random and normal. Now, obviously, if it wasn't, it means that we can't actually use this process. There'd be a different process to use, but I don't cover that in this series of videos. All right, our null is that the difference is the same, or I should say that basically in this case, that there is no difference. So what we're assuming here is that the initial value or the initial difference is 0. Okay. What we're curious to know is whether or not that reading program improved their scores. So we're looking at the mean of the differences being greater than mu0. All right. So T is the mean of the differences, which is the 3.4 that we found earlier. Again, we're assuming 0 here for mu0, divided by the standard deviation of 4.393, divided by the square root of 5, which is the sample size. That gives us a t-score, t-value of 1.731. Our df is 4, 5 minus 1. And so again, using the table, we would have p between 5% and 10%. Okay. Now, in this case, we were using a alpha value of 0.05, and so we actually are not going to reject mu in this, or the null in this case. P is greater than 0.05, so we fail to reject the null. We do not have convincing evidence. We do not have convincing evidence that the reading program improved or increased reading scores. So again, what's kind of interesting is when you look at the data, there was a difference, right? The students' scores, for the most part, did increase anywhere from, well, you had the one student who went down, but otherwise they increased anywhere from 1 to 8. But our statistical analysis shows that those differences weren't enough to show an actual or statistically significant improvement in their reading scores. Okay, let's do, again, one more example of this type. So again, I would encourage you to try this one on your own and then start up the video again to see if you did that correctly. So it says, researchers designed an experiment to study if caffeine withdrawal leads to increased depression. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, or other substances with caffeine for the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake. During another 2-day period, they took placebo capsules. The order in which subjects took caffeine and the placebo was randomized. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine leads to an increase in depression at the 5% significance level. Okay, that was a lot. So basically, 11 people who are known to be dependent on caffeine are basically put through this experiment where for 2 days they have caffeine, for 2 days they don't, but they don't know which order they're getting the caffeine and the placebo. And the question is, do we see that the actual withdrawal of caffeine on those 2 days with the placebo is causing an increase in depression? All right, so we've got their data. We have kind of how they rate their depression level um, with caffeine and how they rate it without caffeine. And so again, we need to start by looking at the differences between those two different samples. So we're just going to we'll do caffeine minus placebo here. We'll just do it in the order listed. So we're going to go minus 11, negative 18, negative 1, negative 4, negative 6, negative 19, negative 6, negative 3, negative 13, negative 1, and the last person coming out actually on the other end of positive 1. So again, like before, I'm just going to encourage you to use some technology here. And find your mean and standard deviation. So the mean of those differences, if we add all those together, divide by 11, would give us negative 7.364. And our standard deviation of the differences is 6.918. Okay, so again, as we look at the data, we have evidence that there is a difference. We have evidence that depression was actually lower while they were on caffeine and higher when they went off of it. The question is it statistically significant? And that's the whole purpose of this hypothesis test. So we have our checks. Again, we are just going to assume normal and random. In an experiment like this, it's a little bit different, like the reading program. So we're going to assume, just for the sake of being able to move on and do the problem, that we have random and normal, but we always want to check for both of those. All right, our null is that the difference is, again, we're going to assume equal to 0. We're going to assume that this is 0. In this case, we are wondering if the difference is less than 0. Okay. All right, t is negative 7.364 minus 0 divided by the standard deviation divided by the square root of 11, our sample size. That gives us a t-value of negative 3.53, and our df is 10. So from the table, we have 0.0025 to 0.005. So very, very, very low p-value, right? We're at 0.25% to 0.5%. So we're less than 0.5% here. P is clearly less than 0.05. We reject the null. We have convincing evidence. Let's see, how do we want to say this? That basically caffeine withdrawal increases depression. Caffeine withdrawal, again, at least according to this data, increases depression. All right. So that is how you do a difference of means, and obviously earlier the mean of the differences. Excuse me, that was mean, getting myself mixed up here. That was mean of differences, right? We take the mean of all those differences. Earlier we looked at the difference of the means, subtracting the two means of the two different samples. So let's finish up now, excuse me, by looking at the proportions. So we're going to do the same process, but now we are going to get into proportions rather than means. All right. And so here we've got the similar assumptions. We've got independent random samples. Remember here now with proportions, we're looking at the kind of the ratio of the sample size to the population. We want to make sure that our sample is less than a 20th of the population, or that the population is 20 times larger than the sample. That we've got two distinct groups, and that both samples contain at least 10 individuals in each of the categories. Okay, so there's a little bit more to think about here because we've got two different samples, but the checks are the same as what we did in the previous lesson for the one sample hypotheses. Just having to kind of look at it a little bit more because now we've got the two samples. So we're going to start, as always, with our after we go through the checks with our hypotheses. So here, like the mean, we're going to assume that the proportions are the same, or if you'd like to think of it this way, that the differences are 0. And then the alternative, as always, is that that P1 is either less than, greater than, or not equal to P2. Proportion, we're back to Z. So typically you use T when you're finding a mean, use Z when you're finding a proportion. The exception to that is again, if you know the population standard deviation for a mean, you would use Z. But typically for a mean, you don't know that. Typically you're using T. So we're taking statistic minus mean. Just kind of bring us back to our roots of what this formula is really finding. Statistic minus mean divided by the standard deviation. So in this case, with proportions, we're taking P1 hat minus P2 hat. So those are the difference of the sample proportions, minus P1 minus P2. But again, from our assumption, or from our null hypothesis, we're assuming that that's just going to be 0. And then dividing that by the square root of P1 times 1 minus P1 divided by N1 plus P2 times 1 minus P2 divided by N2. Okay, now let's talk about this a little bit more here. So in order to find the standard deviation, we would need to know the population proportions P1 and P2. Okay, let me write that down. To find standard deviation, we need to know. I'll just say it this: we need to know P1 and P2, right? We need to know those population proportions. All right. If we knew the population proportions, we wouldn't even have to do this test. We'd already have our answer. We know whether or not P1 is less than or greater than or not equal to P2. But we sample, right, to make an inference about the population. So we don't know P1, P2. All right. So because of that, we are assuming, right, that P1 is equal to P2 as our null, right? So we assume, P2 is over here, that we assume that P1 is equal to P2 by the null hypothesis. All right. If you look at the formula for Z, okay, we're basically in the denominator, we are assuming in essence two different values for P, right? We're assuming that a P1 and a P2. But if our actual assumption is that there is no difference, then it wouldn't make sense to use different P values in that denominator for standard deviation. And because we don't know P1 and P2, if we knew P1 and P2, we could plug it right in and we would use different values, but we don't know those. So what we do is we assume that they are the same value. And the way that we're going to find that value is we are going to find what's called just P hats. It's not P1 hat, it's not P2 hat. So it's a combined what we call pooling proportion, okay? And what we're going to do is we're simply going to take x1 plus x2 divided by n1 plus n2. Okay. In other words, we're going to take the numbers that we would use to find the proportions, add those together, and divide by the pooled sample size. So this is called a pooled proportion. Okay. I know that doesn't make a lot of sense right now, and I'm not explaining it very well, and I apologize for that. When we go through an example, it'll make a lot more sense. Okay. We're going to find this thing called a pooled proportion. And what that does then is it changes our formula. Because now, again, assuming that P1 minus P2 is 0, we don't really need that second part. So I'm going to simplify this quite a bit. The numerator then just becomes the difference in the proportion, the sample proportions. In the denominator, I'm going to write this two different ways, but instead of P1, P2, we're just going to use this P hat. So I'm going to take the square root of P hat 1 minus P hat divided by N1 plus P hat times 1 minus P hat divided by N2. Okay, so it's the same structure as the formula that I gave you earlier. It's the same structure as that formula at the top of the screen. The only difference is, again, instead of using P1, P2, which we don't know, we're going to use this pooled proportion P hat. Okay, now, if you wanted to, you could rewrite this differently. And I'm not going to really kind of go through the math of how we got to this point. But if you wanted to, and I actually prefer the first method because it's the same as kind of what we do in other situations. So it's got a similar structure, so I can remember it more easily. But you could, if you wanted to do this, basically, if you factor out the numerator, you would just have the P hat 1 minus P hat in the front, and then 1 over N1 plus 1 over N2. So we're just really factoring out the numerator to get this, but you could write it like that and think of it that way as well. And like I said, I know many people who like that second formula better. It's actually, it is more efficient. You're welcome to use whichever formula because they will both give you the same answer. Okay, so according to phys.org, Hispanic females are underrepresented in STEM programs compared to non-STEM programs. A certain university would like to see if this is true for their students. They took a random sample of 300 STEM students and found that 12 were Black and Hispanic females, or Hispanic females. A separate random sample of 500 non-STEM students had 75 Black or Hispanic females. Do the data provide convincing evidence that Black and Hispanic females are underrepresented in STEM programs using the 5% significance level? Okay, so let's start with our checks. So again, different checks than when we do the mean. We again want to make sure we've got random samples, which this one does tell us we have random samples, so we're good there. Again, we want to make sure that our population is 20 times greater than the sample size. Now, again, some textbooks will use 10% as its threshold instead of 20%. Basically, we just want to make sure that we have a small sample size compared to the population. And again, I've said this in previous lessons, but I'll say it again. It does not mean that we want small sample sizes. We always want the largest sample size possible. If our sample size is large enough, though, we have to switch to a different method. We can't use this method if our sample size is too large. So it's not that we don't want the small sample size, it just restricts us to using this method, okay? So in this case, in order for this to be true, our population would have to be equal to, or excuse me, greater than or equal to 50 or 500 times 20 or 10,000. Okay, so we're at a university. Some universities are obviously smaller than that. We'll assume, again, for purposes of this, that we are greater than that threshold, and then we need to make sure that our samples are greater than 10. Well, clearly they are. We've got 300 in one sample, we've got 500 in the other, and so again, we are good to go there as well. All right, so our checks are done. We can go ahead and move on to our hypotheses. Our first hypothesis, our null hypothesis, is that there is no difference, that P1 is equal to P2. And again, like with means, we want to make sure that we define these proportions. I'm going to define P1 as Black and Hispanic females in STEM programs. And we're going to define P2 as Black and Hispanic females not in STEM programs. Not in STEM. So using those then, our alternative is, again, is there convincing evidence that they are underrepresented? So in this case, is P1 less than P2 is kind of our question. And again, we could switch that around if we wanted to. All right, so we have to find P hat, right? We're going to do this pooled proportion before we get into actually finding Z. So P hat is going to be, so we take the 12 plus the 75. We've got 12 Black or Hispanic females in STEM, 75 who are not. That's the N1 or the X1 and the X2 that we're adding together. So we're going to take 12 plus 75 and then divided by the two sample sizes. So what we're doing here is really saying, look, if we don't care about STEM, not STEM, right? If we just want to know how many, in this case, really just what is the proportion then of Black and Hispanic females at this university? So we're looking at it, or from the sample, we're looking at 12 and 75. So there's a total of 87 Black or Hispanic females who are part of the sample. We divide that by the total of the two samples, 800, which means that as a group in this sample, in this combined sample, they represent 10.9% of the people in the sample. Okay. All right. So that's the P hat, and then we also need to find P1 and P2 because that's going to be obviously the proportion for each. So P1 is the 12 females who are in the STEM program, which represents 4%. And P2 hat is 75 divided by 500, which represents the proportion of Black or Hispanic females not in STEM programs, which is 15%. So again, just right here, we have some evidence that they are underrepresented, right? If I look at the demographics of those in the STEM program, only 4% are Black or Hispanic females. If I look at the demographics of those not in STEM programs, 15% are Black or Hispanic females. So we clearly see a difference in the data here. Again, the question is it statistically significant? So let's go ahead and find Z. Z is P1 hat minus P2 hat divided by the square root of P. I'm going to use, so again, I mentioned that there's two formulas up here. My personal preference is the first one, but I think I'm going to do the second one just because if you haven't kind of set a preference yet, if you haven't done this before, I think maybe the second one might be a little bit easier for you to grab onto. So I'm going to use that one. Let's do 0.109. That's the P hat, right? That's our pooled proportion, times 1 minus that number, and then times 1 divided by each of the sample sizes. So 1 divided by 300 plus 1 divided by 500. And clearly I needed to give myself more room for that. That gives us a Z value of negative 4.833. Okay, so again, in the table, we find that we're off the table. If at least most tables, you're going to be way off. Remember, Z-score is how many standard deviations you are from the mean. So we're almost 5 standard deviations away from the mean. That is really, really far away, statistically speaking. P is basically 0, all right? Which basically then means that obviously P is less than the 5% threshold that we're using. We reject the null. We do have convincing evidence. We have convincing evidence that we have convincing evidence, getting ahead of myself here, that Black and Hispanic females are underrepresented in STEM programs. And I'm going to say specifically at this university, right? Because our sample was only from this university. So when we think about the idea that we sample to make an inference about the population that I'm able to infer to is the population from which we took our sample. So I can't say that this is true across all universities. I can only say that it's true for this university. So in STEM programs for this university. If another university wanted to know if it's true for them, they'd have to take a sample of students from their own university and do a similar process. Okay, last example for this lesson, we're going to do one more proportion. To study the long-term effects of preschool programs for poor children, researchers designed an experiment. They recruited 123 children who had never attended preschool from low-income families in Michigan. Researchers randomly assigned 62 of the children to attend preschool, which was paid for by the study, and the other 61 to serve as a control group who would not go to preschool. One response variable of interest was the need for social services as adults. So that's kind of the question here is, does one group need more social services than the other group as adults? Over a 10-year period, 38 children in the preschool group and 49 in the control group have needed social services. Do these data provide convincing evidence that preschool reduces the later need for social services for children like the ones in this study? Okay, so our checks. Again, we're going to just assume the random. It was random assignment, I believe. I think they told us that. I guess they don't say, do they? Oh, yeah, they do. Yep, we have random assignments, so that's good. All right, so we are random. Total number of children. So again, when we're looking at population, right? If you look at all the children, I guess we could say all the children in Michigan where this study was done, that has to be greater than 20 times the number of children in the study, which is 123. That's 2,460. I think we can assume that there's more than 2,460 children in Michigan. So we'll assume that checks. We have 61 children in one group. We have 62 children in the other group. So that tells us that we're good there. All right, let's go to our hypotheses. The null, again, we're assuming that there is no difference, that regardless of whether or not children were in preschool, they are going to need the same amount of social service support. But P1 specifically, we will say these are the children in preschool. And P2 is the children not in preschool. I'll just say not in preschool. Okay. So again, like before, we're going to find P hat, P1 hat, and P2 hat. So P hat is, we had a total of, we had 38 who needed services and 49 who needed services. So 38 plus 49 divided by 123 total who were part of the study. And that's going to give us 0.707. So basically, again, regardless of whether or not they were in preschool, 70.7% of the participants needed social services later in life. Okay. P1 hat is 38 out of the 62 who were in preschool needed social services. And P2 hat is the 49 out of 61 who were not in preschool, but also needed social services later in life. Okay. All right, so Z is 0.61. I think it should be a 3, not a 2. My apologies. Back at P1 hat, that should be a 613. So 0.613 minus 0.803 divided by, and I think I probably did it again, probably didn't give myself enough room here. We've got 0.707, 1 minus 0.707, and then times 1 over 61, 61 and 62, so 61. I guess 62 technically is N1. It doesn't matter, obviously, which order we do this in, but to be consistent, I'll put 61 and 62 in the right order. Okay, that gives us a z of negative 2.31. And again, from the table, that gives us a p of 0.0104, so about 1%, okay, which is clearly less than 5%, and therefore we reject the null. We reject the null. We have convincing evidence. We have convincing evidence that attending preschool reduces the need for social services later in life. Later in life. Okay, so that is how we do a difference of proportions. And that takes us to the end of this lesson. I hope that was helpful. I hope that made sense. Thank you for watching, and I look forward to seeing you in the next one.